The presence of inductance in electric circuits can radically change the operating characteristics. Therefore, it is vitally important that we achieve a good working knowledge of the inductor in a series circuit arrangement. One method for finding certain values is called vector analysis. Let's begin by using this method then to find total impedance of this series configuration. To find the total opposition or total impedance, we must find the values of R and X sub L. Now, of course, our resistance is given at 9 k ohms, while we must compute the value of inductive reactance. Since we have the value of L and the frequency applied, we can use this formula to determine inductive reactance. 2 pi times the frequency times the inductance. Multiplied out, we would find that the X sub L for our circuit is 12 k ohms. Our next step would be to plot these values as vectors on a graph. The resistance vector is plotted at 0 degrees. If each block on our graph represents 1,000 ohms or 1 k ohm, the resistance vector would be 9 blocks long for the 9 k ohms of resistance. Our next step would be to plot the 12 k ohms of inductive reactance. This 12 k ohms of X sub L is plotted at 90 degrees. Now, this would be due to the voltage-current relationship through any inductor. To find the total opposition, then, we construct a parallelogram and then connect these two corners. Then, with the same unit of measure that we used for constructing our R and X sub L vectors, we measure the physical length of the resultant vector. This vector then represents the vector sum of R and X sub L and is the total opposition in our circuit. And in our example, we have 15 units or 15 k ohms of impedance. Now, you'll notice an angle is generated between the impedance and the resistance vectors. This angle in here is known as the impedance vector. The impedance vector in an inductive circuit is positive, which tells us the impedance vector lies in a counterclockwise or positive direction from the resistance vector. If we had a protractor, we could actually measure the number of degrees in that impedance angle. Now, we know, being an inductive circuit, the impedance angle will be somewhere between 0 and 90 degrees. If we'd have measured ours, however, we'd have found it to be approximately 53 degrees. That is, a positive 53 degrees. By establishing the total impedance in our circuit, we can now determine the amount of current that is flowing and the voltage drops across the resistor and across the coil. Using Ohm's law, we know that current is equal to E, or the voltage applied, 300 volts, divided by total impedance, which you'll recall is the vector sum of R and X sub L, or as we found on our vectors, Z is equal to 15 k ohms. 15 k ohms divided into 300 volts would give us a current flow of 20 milliamps. Now, this 20 milliamps, of course, must flow through the 9 k ohms of resistance. Therefore, the voltage across R is equal to I times R, or 20 milliamps times 9 k ohms, or 180 volts across R. This 20 milliamps flows also through the inductive reactance, 12 k ohms, of our inductor. And the voltage across the inductor would be equal to 20 milliamps times 12 k ohms, our X sub L. Or 240 volts would be dropped across the inductor. Now, these voltages that we just determined with Ohm's law cannot be added algebraically. For remember, they are occurring at different times or are out of phase with each other. Plotting these voltages as vectors will emphasize this point. Since the voltage applied to our circuit is the only value in our circuit that doesn't change, we're going to use it as our reference vector. Therefore, we're going to plot 300 volts of E applied at 0 degrees. Before we go ahead with the vector diagram, I'd like you to recall that when we constructed our impedance vectors, that the impedance angle was a positive 53 degrees. Well, the phase angle in a reactive circuit is the same as the impedance angle, except the sign is opposite, or it would be a negative 53 degrees. Of course, we know we have an inductive circuit. We know there's going to be a current lag. So the current then, 20 milliamps, would have to be plotted here, lagging the voltage applied by 53 degrees, or at a negative 53 degree angle. As you remember, the voltage drop across any resistor is in phase with the current that's flowing through that resistance. Therefore, ER, 180 volts in amplitude, would have to be plotted in phase with the current, like we see here. We know also that the current flow through any inductor lags the voltage by 90 degrees, or the voltage leads the current by 90 degrees. Or since we're plotting the voltages, the voltage across the inductor would have to be 90 degrees in a leading or positive direction from the voltage across the resistor or the current. Therefore, EL would be plotted at approximately 37 degrees. And you'll recall from Ohm's law, EL is equal to 240 volts. If we then constructed a parallelogram from the inductor voltage and resistor voltage vectors, we would find that the resultant vector is the 300 volts, the voltage applied. And of course, here is theta, the phase angle, current lagging the applied voltage by 53 degrees. Now, constructing these vectors may not be considered the most accurate method for finding these values, but it is indeed descriptive of the actions that are taking place in our circuit. Another useful device in interpreting the series RL circuit is the oscilloscope. As you can see, the oscilloscope that we are using has two traces. We can apply different signals to either trace. This way, we can actually compare the voltage across the resistor with the voltage applied. And we can compare the voltage across the inductor with the voltage applied. To the lower trace, we have already applied the voltage applied. The waveform above is the voltage across the resistor in an RL circuit. First of all, we can check the relative amplitude by moving the lower waveform up. And of course, we can see that the voltage applied is greater in amplitude than the voltage across the resistor. You'll also notice there's a definite phase difference. If we move the waveform down just a little bit, you'll notice that the voltage applied is reaching a maximum positive value before the voltage across the resistor reaches its maximum value. Well, this indicates to us that the voltage applied is leading the voltage across the resistor by some degree. This, of course, you recall, is what we found when we plotted our vectors of these voltages. Well, if we change our leads quickly, we can also determine the voltage across the inductor, or compare the voltage across the inductor, I should say, with the voltage applied. Remember now, the voltage across the inductor should be leading the voltage applied. Okay, below again the voltage applied and above the voltage across the inductor. And to check the relative amplitude quickly, we move the waveform up. Notice again, voltage applied is greater than the voltage across the inductor. But you'll also notice another phase difference. Only this time it is the voltage across the inductor which is reaching its maximum value right here sometime before the voltage applied reaches its maximum value. So this, of course, proves, just as we found in our vectors, that the voltage applied leads, or I should say, the voltage across the inductor leads the voltage applied, while the voltage across the resistor lags the voltage applied. Well, we've constructed vectors, and we've used an oscilloscope. But there is still one more method, a very accurate method, for obtaining values in a series RL circuit. That is, understanding how trigonometry and associated mathematics can be used to solve for total impedance, phase angle, and so on. It cannot be overemphasized that this is a simple approach if, and only if, the technician has properly condition himself as to the use of the trigonometric functions and the trig table. For instance, if we wanted to find total impedance, we could picture the original vectors that we constructed, our resistance vectors, R 9 k ohms, X sub L 12 k ohms, and the resultant vector 15 k ohms. You'll notice that the resultant vector Z actually divides our parallelogram into two right triangles. We can find the hypotenuse of this right triangle here if we know the values of the other two sides of that right triangle. And of course we do, because this side would be equal to 9 k ohms, and this side here would be equal to the inductive reactance, 12 k ohms. Knowing these other two sides, then, we can use Pythagorean theorem to determine total impedance. Pythagorean theorem says that the impedance is equal to the square root of the resistance squared plus the inductive reactance squared. And of course, if we substitute our values, which you'll recall were 9 k ohms and 12 k ohms, we would find that impedance would be equal to 15 k ohms. Now, of course, you'll remember that this was the same value we found when we actually took the impedance vector and measured it. Trigonometry is not limited to finding the impedance. It can also be used to find the phase angle, for instance. The cosine of the phase angle, or the cosine of theta, is equal to the adjacent side of the right triangle we were just talking about, divided by the hypotenuse of that right triangle. So if we used our voltage vectors instead of our resistance vectors, we could say that the cosine of theta is equal to the adjacent side, which is 180 volts ER, divided by the voltage applied, which would be 300 volts. 300 into 180, of course, equals 0.6. Our next step would be to refer to our trig table. There we can find this number and its associated angle. Now this is the portion of the trig table that we need. All we have to do is to move along the cosine positions on the left until we find the closest cosine to 0.6. In our case, it would be 0.6004. Our phase angle, then, is 53.1 degrees. That is, as you recall, a negative 53.1 degrees. And remember, this tells us that the current is lagging the applied voltage in our circuit by 53.1 degrees. Not only can we find total impedance and total voltage and phase angle with trigonometry, we can also find the power factor. You recall that the power factor is equal, for one, the ratio of ER to the voltage applied. And just a moment ago, you'll remember, we used this same ratio for our phase angle to find the cosine of theta, or our phase angle. So naturally, the power factor must also be equal to the cosine of theta, or the phase angle. Well, knowing this, we can again use our trig table, this time to find power factor. If we know the number of degrees in our phase angle, then we'll use the same angle, 53.1 degrees. Then, of course, it would be simple to find the cosine of that angle, which, of course, would be 0.6004, or 0.6. Another commonly used ratio to determine the power factor is true power divided by apparent power. True power is the power that is actually being used up or being dissipated in our circuit. Now, since the resistance in our circuit, our 9 k ohms of resistance, is the only component in our circuit capable of actually dissipating any power, then true power would be the current squared times the value of that resistance. Or substituting our values, you recall 20 milliamps times 9 k ohms. And this tells us, of course, that true power is actually 3.6 watts. Now remember, 3.6 watts is the total power that is actually being used up or consumed in our circuit. Apparent power, on the other hand, is the total power actually being supplied to our circuit by the source and is not necessarily being completely dissipated. We find this, in our case, by taking the applied voltage, which is 300 volts, and multiplying it by the total current that is flowing, which is 20 milliamps. Now, if we substitute these values into our formula for apparent power, we find that the apparent power in our circuit, which is equal to current times voltage, is equal to 20 milliamps times 300 volts, or an apparent power of 6 volt amperes. Well, we know the true power. We know the apparent power. Let's go back then and substitute these values into our original formula. Power factor then would equal a true power of 3.6 watts divided by an apparent power of 6 volt amperes. Or, of course, dividing out, power factor would, just like the cosine of our phase angle, equal 0.6. Well, we've talked about vectors, we've constructed vectors, we've talked about measuring vectors. We've also used an oscilloscope, and we've compared the relative amplitude and the phase of signals in an RL circuit, a series RL circuit. We have also found the power factor by using trigonometry, as well as total impedance. Now, it may be impossible for you to fully appreciate these maneuvers at this stage of your study, but we must become knowledgeable of the simple circuit before we could possibly challenge the more complex circuit. So long.